All right. Hello, everyone. Welcome to today's webinar. Happy Friday. Thank you for making time to be here. I'm going to go ahead and get us started right at the top of the hour here. I know Howard has a really packed presentation for us today, so I'm looking forward to that. My name is Heather Grant. I am one of the community admins in the maintenance community by Upkeep. Thank you once again for being here with us today. If you're not already a member of the maintenance community on Slack, we would love to have you join us. I will add the link on how to sign up in the chat in just a moment. Today, we have Howard Penrose from MotorDoc LLC joining us for a presentation on electrical signature analysis. I am looking forward to learning a lot. The recording from today's session will be available in the maintenance community Slack either later this afternoon or on Monday morning, along with a copy of the slides that you see here today. Howard himself is also available to answer questions live in the Slack group, so please feel free to share the recording of this webinar or the invitation to Slack directly with friends, colleagues, or anyone else you know who would benefit from hearing some of Howard's expertise. Last piece of housekeeping, and then we'll go ahead and get started. You'll notice that your cameras and your microphones are not turned on today. So if you want to ask any questions of Howard throughout the presentation or answer any that he may ask you, please use the chat feature on the right-hand side of your screen here. Feel free to chat hello and chat your questions as they come up throughout the presentation today. If we have time at the end of our presentation, we'll answer any questions that we can. If we do not, we will answer those offline in the community as well. That is it from me. Thank you, Howard, for being here. Thank you once again, everyone, for joining. And Howard, I'll turn it over to you to get us started.
Great. Thank you, everyone, for joining. Hopefully you find this educational, especially if you've only become aware of electrical signature analysis. I'm going to do kind of a good solid dive into the technology. Quick overview. This is a shorter version, see if I can get everything going, of longer courses that I do. But just to give you an idea, we're going to kind of do a quick overview into the technology. Then we're going to get into how the technology in general, meaning that I use a specific technology, others out there will use different ones. This covers everybody. So that's one of the nice things about electrical signature. Then we'll go into the electric machinery itself. We'll talk about the driven equipment, and then I'll get into how to identify energy improvements directly by defect within the technology, and then kind of introduce you to some of the research we've been involved in, because right now MotorDoc remains the leading researcher, everything from artificial intelligence and machine learning in this technology to identifying problems. So we'll go ahead and start. So one of the nice things about the concept of electrical signature analysis, and I'll cover what that is a little bit more. If you've heard the term motor current signature analysis, you're no stranger to this either. But the concept was developed back in the late 1980s at Oak Ridge National Labs by Howard Haynes, and he had looked at a method for detecting motor-operated valves in the nuclear power industry. This is not to be confused with motor current signature analysis, which was developed through Bill Thompson at the University of Edinburgh for offshore drilling rigs in the North Atlantic. So they were developed in parallel. One takes a little more work to understand what's going on. Electrical signature I kind of prefer because it gives me a look in both directions. So if I look... don't know if my arrow is going to show up. It does. Great. So if I take data in electrical signature analysis in both voltage and current right about the motor control, or if this is a generator, in particular voltage signature analysis from the point between control and stator, I can look both directions. That means I'm looking upstream up to and including the transformer, and I'm looking downstream all the way to the actual load and process. To put this in perspective, a lot of people know me for doing wind turbines, one of the most complex systems that you could probably do with this. And we look at the condition of the transformer, the generator, coupling, the gearbox, which is 3 stages and a large planetary gear set, and main bearings, which are turning between 14 and 20 RPM, and the condition of the blades in about 48 seconds. So it's a solid system technology versus something like vibration, ultrasound, and some of the other technologies that are point test, meaning I will test if I'm looking for a bearing, I test over that bearing and I see that defect. It does mean there's some trade-offs. So don't get me wrong. This is not, there is no one technology that does it all, but it does help identify a lot of things. It will detect mechanical issues, later stage, and so on. So the concept behind electrical signature analysis is to look at current signature analysis, which starts at the point of test downstream through the load if I'm testing a motor, and voltage signature analysis, which tests from the point of test upstream through the transformer. Or if I'm testing a generator, current signature analysis goes to the transformer, voltage signature analysis goes to the powertrain and generator. Motor current signature analysis was always defined as just looking at things like rotor bars. I kind of joke about that because in the early 1990s, as a vibration analyst, when I'd go out and test a motor to see if it had broken rotor bars with vibration, if I wasn't sure, I pulled out a $50 analog clamp-on ammeter, clipped it around the cable, and watched for a ticking motion. Now I can spend $28,000 to do the exact same thing. So if you're looking for broken rotor bars, probably not the type of technology you want to emphasize, only because that is really simple. So all of the other stuff we look at is very important. And then, of course, you're looking at power quality. Okay, if I'm doing just current readings, I'm looking at specific types of power quality. When I look at both, I can look at harmonics, and I can look at kilowatts, and I can look at torque, and I can look at all of the other things that tell me everything that's going on using the machine itself, the air gap, as my transducer. So when this is a Howard Haynes cartoon, I stole it. I know him, but I stole it because it was kind of cool. Doing vibration analysis work still as well. I know the fun of going out to the machine, climbing over it, getting data, and versus walking into a motor control center and grabbing data there. The challenges I run into with the technology is most of it is spectral analysis, meaning just like vibration. As a matter of fact, when we look at this, if you're a vibration analyst, all you need to do is stand on your head and cross your eyes and you're looking at the same thing. When I do a motor control center, it's opening the cabinet, accessing power, or you need an e-plug or something to plug into in order to gather the data. And mechanical engineers and mechanical technicians that tend to be the vibration analysts really don't get along well with electricity versus an electrician who doesn't always have that training on how to look at a spectra or an FFT. So those are probably the two biggest differences, and the FFT part and accessing the voltage and current that I need are probably areas. Is not this the same electrical circuit? So I just got a question. Current signature and motor current signature analysis. It is, but motor current signature analysis tends to look at a very small spectral range and emphasize just the machine. Current signature analysis actually looks at the entire load and process as well. I'll show you that as we go through. So we talk about the machine. This is just an induction motor cutaway. You can do it on any type of rotating machine, anything with a magnetic field, basically, up to and including a transformer. So in an electric machine, we're taking data primarily, even when in an AC machine, I'm taking it from the stator fields. In an armature or DC machine, I'm taking it from the armature, the load carrying portion of the machine. So I'll take data on this side. Well, because I can't really take it on the rotor, but in any case, I do see the rotor indirectly. And what we do is we use the air gap, that area between the rotor and the stator. That is my transducer right there. So everything is done through magnetic field. And if you think of it in those terms, it kind of changes how you look at the diagnostic. So if I'm looking at a machine and I've got a good air gap, and I've got my fields in between. I have a nice sinusoid coming in of voltage. I will have a nice sinusoid coming out of current. The challenge will come if I have noise in my voltage coming in. Then I will see a reflection of it depending on how well tuned my system is. I'll see that reflected in current. So sometimes I'll see peaks here, and actually they come from a machine nearby. So I like to take voltage and current so I can separate where my problem is coming from. The primary thing we're looking at in virtually everything is what's going on in the air gap. It's going to be side-to-side vibration in the air gap, or in this case, static eccentricity, the rotor kind of off to one side and running. Another one would be orbiting, which is dynamic eccentricity. I'll show that in a second. But in any case, that side-to-side movement, because I'm dealing with something called the inverse square law of fields, it only takes a small movement, a few thousandths of an inch, or a fraction of a millimeter for those overseas, to detect what's going on. And that frequency rides upon my sine wave, my 50 or 60 hertz coming in. The other one is dynamic eccentricity. That's the orbiting of the rotor inside the air gap. Now, that could be, as shown here, the physical orbiting, which hopefully it doesn't orbit this much, or the motor isn't running anyways. But this orbit within the air gap can also be magnetic orbit, meaning that my motor could be dead center, but if I have a number of broken rotor bars on one side, I'll have an unbalanced magnetic field and it'll orbit within there, and I'll see that in addition to your common rotor bar faults, I will also see that as dynamic eccentricity. Different effects occur on the shaft that I would see from a motor perspective. That includes unbalance. That would include torsional issues, meaning something on the shaft that's causing torsional feedback. I will see misalignment or mistensioning of belts. And hot spots on the rotor will often show up. Now, I've just actually put together the paper, the presentation on the paper this morning for IEEE, because nobody had ever done the formula for missing wedges and coil movement in a stator, although we all know how to do it. So we went ahead and put together a paper today. So not just the rotor, but stator issues as well. Everybody ignores the stator for some reason. Unlike vibration, I have a carrier frequency. So I have an amplitude modulated signal that I follow. And that'll be in both voltage and current. I have something simulating a sine wave. And that sine wave is the carrier frequency of all of the defects I'm looking for. Now, if I'm just looking for straight harmonics, and I add, say, 300 hertz to that, it'll cause, variation to what the sine wave would look like. And that 300 hertz would then, if I pull those out into an FFT, which means amplitude versus frequency, in this case, I'd have a 60 hertz, and then out here I'd have a 300 hertz for that fifth harmonic. In any case, at 60 hertz. In any case, this amplitude in vibration, we usually look from the base up. So if I'm looking at acceleration, or I'm looking at velocity, or I'm looking at displacement, that's some value from here up. In the case of electrical signature analysis, I'm looking for some peak down to the next peak. So I'm looking for a relationship there. It does provide something very interesting for those who do vibration. You'll understand that if I go in and I do a test and I'm at 20% load, and I come back and I do a test at 75% load, I actually might have some big changes. In electrical signature analysis, that's not the case. At 25% load and 75 and 100% load, my values are going to be roughly the same. When I convert it over to a relative force, and we'll cover that in a few minutes. Things to consider when I do electrical or current signature analysis is electrical safety. If I access a machine, I have to be aware that there is voltage and current present. So there are different devices depending on the manufacturer for what we refer to as my technology we refer to as e-plug, but they have different names. It's the same thing, where it's all contained within the cabinet and you have some reach out to outside the cabinet to allow you to plug in your data collector, assuming you're doing data collection. You also do the same thing for the continuous monitoring versions of the technology, where you would do the same type of thing. You and the video are talking over each other. Should not be any talk from the video. Equipment information I need includes things like the power, the voltage, current, and the speed. I absolutely need those to do a proper analysis. It's nice to have the remaining nameplate, meaning other information from the nameplate, including the number of rotor bars and the stator slots. Those are vital if I'm going to do a more in-depth analysis. In addition, bearing information, because you can detect bearings with the technology. Rotor bars and stator slots, depending on the type of thing, if you have access to a database either within the software for the technology, or if you do vibration, or you can even go to online catalogs of the different bearing manufacturers to get the multipliers. They're the same. So in electrical and current signature analysis, we use the same multipliers as you would with vibration analysis. And then in the case of the rotor bars and stator slots, if you're lucky, you can contact the manufacturer. Otherwise, you would want to get your repair shops to provide that information as they do the repairs on a lot of the machines. There are some different databases out there with this data. If you really want to copy, contact me later on. I do keep a database. Okay, so what can we analyze with electrical signatures? So if I'm looking at electrical signature analysis, I am looking at current. Okay, so this would be current up top in RMS, current spectra, that's the amplitude versus frequency. And as you notice, everything happens with a line frequency, and there's side bands. There's peaks on either side of that. They're mirrored. Now I can demodulate it, whether I'm looking at voltage, current, I demodulate it in order to look and see what those individual peaks are in actual value of current. The important thing to remember here is the amplitudes that you see here may not reflect when I'm doing it in decibels, which is the common method, the common measurement that we do. So each of these peaks, I'll measure from my peak, in this case, line frequency current, down to this value down here, which looks to be about -60, whatever this sideband is. And you notice there's a mirror of it on the other side. So I'll count down to that value. So -60 dB or 60 dB down is how we would present it. Higher frequency data, some technologies down here will go out to 300 hertz and that's it. For the data collectors, for Baker and PDMA and Empath and Alltest, you're looking out to at least 5 kilohertz or 5,000 hertz. Some of the technologies allowed you to convert this into RPM or CPM. If you're a vibration analyst and you prefer that, great. Doing both, I prefer looking at my electrical stuff in hertz. In any case, this would be RMS current over a short period of time, RMS voltage. This would be the spectra out to beyond 5 kilohertz. Down here, this one is unique to a couple of the technologies, and this is in kilowatts. Now, the difference here is if I come down here in kilowatts, I'm back to that one time whatever. Up here, everything's going to be in plus or minus line frequency. And it's important to remember, just like in vibration, if I'm testing a variable frequency drive, that line frequency is the output from the VFD. So if I have 60 hertz supplied to my VFD, but I'm operating at 30 hertz, I'm going to be plus and minus 30 hertz, not plus and minus 60. The other one is torque. Several of the technologies do this as well. This would be my air gap snapshot across 10 seconds. And then in here, this would be an FFT torque spectra of that. So I would be able to compare this to some of the other peaks that I'm looking for. And this gives me relative load. Now, this one here we'll return to later on because I can use this to look at, and the kilowatt analysis to look at energy costs by defect, meaning if I have a bad bearing, I can calculate out the kilowatts associated with that, which allowed me to look at both cost, but also greenhouse gas emissions. That seems to be something that's pretty common. Now, a couple of technologies now do continuous electrical signature. And that basically trends, and we'll also do some machine learning work in order to look at defects, the progression of defects, and things like remaining useful life, or the term I use is total time to failure estimation. And yeah, just more data there. So let's get into an example so we can start talking the real stuff. That's an overview of the technology. If you have questions, I can answer them now, at the end, or later. If you've ever reached out to me via LinkedIn or direct email, you know that I try to answer as much as possible. Few important things to remember while we take a look at this. If you look at it in terms of hertz, all hertz is RPM divided by 60, and it doesn't matter where you are. It's always by 60 because it's probably per minute. So in hertz, it's per second. If I want to convert back, I just multiply it by 60. Synchronous speed, or N sub S, is 120 times your line frequency divided by the number of poles. The number of poles is important, small p, because there are other formula, and I don't know if I'm going to cover them in here, but there's other formulas that use big P, which is pole pairs. So instead of saying 2 poles, I would say 1 pole pair. Yes, confusing, but engineering. Slip frequency, this is important because this is the frequency that's seen within the rotor in an induction motor. Not to be confused with a synchronous machine. So in your standard electric motor that is not synchronous, you'll have slip, meaning that the rotor will never quite catch up to the synchronous speed above. So to look at your slip, it's the synchronous speed minus the actual measured running speed divided by the synchronous speed times 60, which should give you a relatively small value. Now, to figure out if I've got a rotor bar issue, I would then figure out what my pole pass frequency is, and that's here. It's just twice this value. Okay, so twice the slip, or you can do the number of poles times the running speed minus the synchronous speed. But this one here is the one that seems to be most common and is in the standards associated with electrical signature, because there are standards. As a matter of fact, there's an IEC standard. Now, when I'm looking at decibels, it is a measurement of relative force. So for decibels and current, it's 20 times the log of the current at the frequency I'm interested in divided by the primary current. And then for voltage, it's 10 times that value. And then that gives me my log value. So when I say dB down, that gives me a decibel value. When I say dB down, that's where that comes from. And I amaze people once in a while by going in and doing the calculation, and boy, it shows up the same, because doing it on a calculator is the same as doing it in software, right? So other things to consider, if I'm looking at stator mechanical issues, there's a complex formula that I can use, or I can go as simple as saying running speed times stator slots plus and minus line frequency. There'd just be 2 peaks associated with stator mechanical. Stator mechanical means a loose stator, missing wedges, or the coil movement, either the coil's moving in and out towards the rotor, or the coil ends moving up and down, say in a startup, or under heavy loads or oscillating loads, or because they're not secured correctly. Rotor indicator, I'm not going to worry too much about that, because that just relates to these guys. There is one error in here. So static eccentricity is running speed times rotor bars, and it's with line frequency and 3 times line frequency, not 2 times line frequency sideband. So it'll be 1 peak on either side, basically twice line or 1 time line frequency part, then a 3 time line frequency, and so on. This error was in here from way, way long ago. Even made it into a few papers, one by me and some by other people. Don't know why. That's just the way it is. But just remember that's 3 and 3. Sorry I didn't correct that before, but there you go. Pole pass frequency is important when I'm taking a look at peaks on either side of line frequency. I'll show you an example in a minute. In that the work done at Oak Ridge National Labs came up with this table. Now the table has not changed since 1989. So there's times when this table is a good indicator and times when it is not. So depends on the application. For your standard induction machine, this is perfectly fine. And here's what it looks like. So this is what I mean. If I put a clamp on ammeter, I'd see the sawtooth, to go tick, 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 tick. But if I put it on a machine, in this case, a 4,000 horsepower, 1,800 RPM, actually 1,790 RPM induction machine. This is there was a band on the end that we removed. You'll see a peak in here. That's at pole pass frequency, and the red line points to another peak, which is 2 times that. And the reason that harmonic exists is because of this good rotor bar here, and then more bad rotor bars on the other side. So if I want to know how many bad rotor bars I have, often they don't just fail next to each other. Often there's a gap, meaning there's 1 or 2 good ones or mostly connected ones, and then you'll have more bad ones. So if I have if I see a second harmonic, I know I have multiple broken rotor bars. If I have 3 and 4, then I know I have a whole lot. In this particular case, 1/3 of the rotor bars were fractured. I have looked at one recently at a site where they were seeing all kinds of broken rotor bars due to manufacturing defects, and some of those had actually lifted out and impacted the winding. Down here, to compare, for those who do vibration, this is vibration analysis on that exact machine. So I have in acceleration the number of rotor bars times the running speed peak with sidebands of twice line frequency. Okay, so the pattern will show up in different ways, but I can confirm this with vibration and vice versa. A lot of people tend not to look out here because this set of peaks can happen at the first harmonic, second, third, and fourth harmonic. In early progression, it'll start on the fourth harmonic and then work its way backwards. So you need to take a broad spectrum in acceleration in order to detect it, or you can use electrical or current signature analysis and see it pretty quick. When we tested that machine, this is actually that machine, you connect, none of the technologies take high voltage. So you need to come off of a CT or PT, and in this case, this is the back of a 489 multi-lin. I'm taking my voltage measurements here, and I'm taking current measurements off of here. I put in a CT ratio, so I think these were 250 to 5 ratio. So I do 250 divided by 5, and I enter that into my CT ratio. And this is normally 120 volts now. So I take whatever the voltage is, divide it by 120, and that puts me in the ballpark. So I believe this one was 35 and 35. So I put those ratios in, and that gives me my true values. Although it doesn't matter. If I'm looking at straight FFT, I don't care what the values are. But to make it look good in a report, that's what we do. So you can take that data from here. Now, what's important when I take data from the back of an energy device like a multi-lin or an SEL or any other device, like even an analog, is not just to remember that, but also remember I am now taking everything off of a second set of CTs. That means I can have a small phase shift or a small amplitude change. So when I expect to see something at this value times this value, say it's supposed to be 60 plus 10.235, I might see 60.9. So if the peak's relatively close when I'm doing something like this, I'll usually count it. So when I'm testing driven equipment, one of the more common ones is a belt application. I need to know things like the diameter of the shivs and the length of the belt. For understanding what my speed range is, if I go from a driven smaller pulley to the larger pulley, say this is a fan on the right, and I'm driving it with a motor, and this is 4-inch diameter to 8-inch diameter, it's literally as simple as saying 4 divided by 8 times whatever this running speed is, and that's the running speed of the fan. Okay, so to understand what the frequency is, if I want to see if I have a belt defect, I would either go to the belt label and see what the value is and know that it's going to be slightly longer due to stretch, or I can take measurements, in this case, twice 40 center to center, plus 1/2 4 pi plus 8 pi in this case, or the diameter times pi and the diameter times pi, half of that, which means that I'm looking at half of this and half of this, and that gives me my belt length. So if I have the belt length, great, I can use that, or if I calculate it, it'll come out to be roughly the same. Then I pick one of these, and I usually pick the motor side because, motors. Running speed times 4 pi. That gives me my conveyor speed. That's the actual speed that belt passes one point. Okay, so once I have those two, I can then divide that belt speed by the length in order to get my belt frequency. And it's kind of fun when you calculate this out and you're doing this technology, because boy, does it come out to exact. Unless you got a lot of slip. And slip's easy to see because the driver, when you have that ratio, will not come out exactly the same. It'll be some peak below where you're expecting to see it, which means you can actually calculate the slip if your belts are loose. The other thing, you can amaze your friends by telling them if their belt is too tight or too loose. If I look at and I see belt frequency and I see the driver driven frequency peak, then I will look to see if I also have static eccentricity. Because if I have belts that are too tight, if all motor shafts deflect, I don't care if it's hardened steel or what, it deflects. So if it is bowed a little bit, I will see static eccentricity, and then I know that I have over-tension belts. Don't get me wrong, you can still have slip in over-tension belts. I just saw that in another site where they had an oscillating load due to their variable frequency drive, so the belt was slipping back and forth on the shivs. And it kind of looks like this. So this is a belt application, and I look at my lower frequency. If I go to my DMOD, I'll see my belt frequency for this particular application is right around 5 hertz. I've got a shiv frequency at about 12 hertz. Something else out over here, this actually has to do with a transformer. And then this peak here, which is my running speed. Now, if I see a high running speed, the values I use are 65 dB down or 10 dB above the noise floor. Once I see those values, I will see it with all other technologies. If I see something below those values, I might call attention to it in critical applications, just so I don't miss it. I'd rather make a false positive, right? So here's my line frequency peak, whatever the actual value is. And what I do is I count both directions. So if I'm looking at my belt, there's a belt peak right there on either side of my line frequency at about 60 dB down and roughly 10 dB above the noise floor. So I'll call and say, you've got an issue with your belts. Usually there'll be some chop around it if it's delaminating, but in general, that means that there's something. It's either slipping or something else. Then I'll take a look at my shiv frequency, which just falls directly on, which means I'm not slipping. If this was actually my driven peak here, then I would say I've got some percentage of slip. But in this case, here it is, dark blue, and I've got a peak on either side. Probably have some shiv wear, especially seeing as I'm about 40 dB down here. Okay, down to 40, there's my 40 dB. Now this comes to something else. You notice this side, the peak is lower, and this side, the peak is higher. It's because I'm using a flat top window when I'm doing this versus a Hanning. I've heard people use rules of thumb to always use the right side, always use the left side. What I have found, because I use multiple technologies, is use whichever side is higher as your value. Okay, so whatever side is higher up, you use that, because one side or the other is going to get some filtering based upon the type of window you use. Okay, so and pre-processing. So when I'm taking a look at this here, this side I'd use, but if this peak is higher, this side I'd use. And then I can take a look up at my high frequency data set and static eccentricity, which we'd shown earlier. So I've got peaks on either side, then more peaks, and then more peaks. And in this case, they fall directly on peaks. Now, what all these other peaks are, that is just line harmonics. Mostly don't worry about them unless you're on a drive and you see something like this. These peaks right here, I refer to as the camel. So depending on the carrier frequency of the drive, I'll have one hump or two. You notice this one here is right around 2,500 hertz. That means that the carrier frequency on that drive is 2,500 hertz. And then I have 2 times the line frequency sidebands on either side, and then twice line. Then this would be basically, so this would be 2, and then this would be 4 times line frequency. That's what those peaks are. I can monitor those. And if I see them in voltage, it also means that I'm seeing a reflection off the transformer, which can cause problems for other machines. This is just a harmonic of that out here. Okay, just something most people have no idea what this is. I'm doing a research project for the wind and solar industry. I know exactly what this is now. Gearboxes, another big opportunity. We do a lot of elevator motors, and those tend to be right angle if I'm looking at a geared application. Speed reducers are relatively common, and there's types like this for cooling towers. Planetary gear sets are for other types of machines. So let's take a look at an example. Here's an elevator, right-hand side. By the way, if you ever do elevators, you'll never get in on an elevator again. So anyways, right-hand side, I've got some value of teeth. So the worm and bull gear type gearbox can be complex. What I end up doing is the number of teeth on the worm gear that match up with the bull gear. So I have 2.5 teeth match up with this bull gear, 108 teeth on the bull gear itself. Believe it or not, we had to count these from a drawing for this particular application. So 2.5 divided by 108, that gives me my ratio times the RPM. That means that whatever my input side is on this worm gear is reduced by 2.5 divided by 108, and then out. For gear mesh, it's the number of teeth times the shaft speed for that particular shaft. If I'm looking at this particular motor here, 25 horsepower, this is the motor from that elevator, 35.7 amps, et cetera, et cetera, et cetera. If I'm able to look down here, I'll see that this is actually a Reliance motor. It might say Schindler on there, but it's built by somebody else. Schindler does not manufacture their own motors, it's actually Reliance. So I was able to go back and get my number of rotor bars and stator slots. So the running speed, 17.56. It's on an inverter. 2.5 divided by 108. I get a 0.406 hertz, which means I better have a good sampling rate on my data collector to get down that low. So if I do this times 60 RPM, that would be the same as 24.4 RPM. So that's the output speed. If I have all my multipliers, I can then go, okay, 17.56, motor speed, each frequency. Outer race, in this case, it says it's bad. They're actually identical bearings. You can see at 6311. The downside of electrical signature analysis, if I have twin bearings like this, I know that one or the other is bad, or maybe both. So those are the frequencies I'm interested in here. Now, one of the things that the different technologies kind of diverge on is the ability to look at a situation like this. So my run on this elevator, Start, hold. So the brake disconnects here, holds, then it runs for a period, then it stops, holds, and then the brake engages. Okay, so I end up with all kinds of stuff because if I were to look for this from the top down, I would have a wavy line frequency. And you notice it doesn't quite hit 60 hertz. So I take a look at this, and what I do is I just evaluate this smooth section here. And when I do that, then everything pops up. Okay, so the two ways of doing this is either with a waterfall or having a technology that allows you to focus in just on that RMS current area where you've got some type of steady. There's some technologies where you just don't get steady ever, such as wind and certain applications in the field, machine tools and the like, where you have to use a waterfall. But in this case, I take a look at this here. There's pole pass frequency, twice pole pass frequency. So I have a lot of casting voids. In a cast aluminum rotor, I'll tend to have casting voids. I'll note them. I won't condemn a machine over it unless the machine's not acting well. The next one is bearings. So here's a cage frequency, and there's my outer race frequency. So those peaks tell me that I have a problem with the bearings, which, at the same time we're audible. So we knew we had a bearing issue. And then, of course, here's a worm gear frequency as well. So we would note that there's some wear and tear on that. And back in that previous slide, let's see if I can go backwards. Those are not bubbles. That's actually brass down in there. That's the machine's wearing pretty well, and they don't change oil very often. So I can then also look to see if I have winding conditions. Now, in inverter applications and others, and I did this paper for IEEE last year, they used to refer to this as the winding short. I've renamed it in IEEE as winding stress, because if I have an inverter and the parameters are not set up correctly, I will see these frequencies. So it's really great if you have a lot of variable frequency drives to make sure that the drive is tuned or set correctly. Doesn't mean I have a motor failure, because what we do when we identify these peaks, and they're small, you notice this is actually one that was called, we went in and changed the parameters on the drive to match the nameplate on the motor, and these peaks went away and everything smoothed out. That one is frequency times integer, 1, 2, 3, 4, 5, usually just use 1, divided by pole pairs. So that's where I was talking about where 2 poles equals 1 and so on. So n over 1, or this could be 1 minus the slip plus and minus k, which is also just an integer, 1, 3, 5, 7, so on. So when I take a look at this times the frequency, I'll end up with a series of peaks. And I usually don't match it up if it's set up over a power frequency, like in this case 60 hertz, 120 hertz. I will kind of ignore that. This is actually not. So this is 55 and 110. So this peak I won't pay too close attention to, but I'll look at these other peaks, and I've got a peak on either side, peak on either side. So therefore I have some winding stress that can be corrected. Right angle gearbox, such as on a cooling tower. The good news is you very rarely can get the number of teeth. So what I do is I look at input and output ratios. Okay, so this is all nasty. I've got all kinds of stuff going on. So I just look at my ratios. This, by the way, is the top of the National Institutes of Health cup. This over here is the big generator that we do as well. But these here are the cooling towers. And we go in and we can take a look. 250 horsepower, 60 rotor bars, 72 stator slots. And then if I look at torque, I've got the fan speed, because I know the ratio, and then these would be gearbox related because I have a rough ratio. And in this case, I actually had number of teeth because, we took one apart. But it came out, if I just put in a ratio of say 1 to whatever this would be down here, then that would give me something. I try to make them integers. And then that would give me an idea when I multiply times speed of different components. That would give me a rough idea. Now, it's harder when I don't have the number of teeth to identify things like the individual bearings inside the gearbox. So if I take a look at that same thing, there's on either side here, this would be the pole pass frequency. That means that the motor has casting voids. So I don't pay close attention to that. These peaks all associate with different components inside that gearbox. We're not quite sure what they are if we don't know the ratios. So all I would ever note is that we've got something going on. And then out here, these would be definitely related to the running speed and the driven equipment speed or the fan speed. So have to remember when I'm looking at the fans, it's the number of blades times the running speed. So back here, it's a lot of blades. Okay, now let's look at this guy right here, 600 horsepower pump on a variable frequency drive, because, you know, why not? They're always on variable frequency drives. It's 480 volts, allowing us to take data directly from the machine. High current as well, because this is a Baldor. Baldor's pretty open with providing their rotor bars and stator slots. We are going to see defects. Why are we going to see defects? Well, it's because, I don't have a good picture of the side, but right here on both ends, they have, for those who are metric, it's about 30 centimeters. Yeah, roughly 30 centimeter foot on either side. For those of the rest of us, it's let's see, 30 centimeter. Yeah, roughly. Anyways, they've got long feet on them and bolt holes on the inside, about midway. So somebody took a shim set, two inches by 2 inches, and put them on the very end, and the bolts go on the inside of that, and then they tighten them down. Well, that of course deflects the entire frame. So we take a look. These are the conditions here in operating. This is torque. It doesn't look too bad, but when I start taking a look at it, I do have bearing frequencies. So I know I have a bad bearing. And okay, well, I thought I had the static eccentricity in there as well. They do have static eccentricity and some slight misalignment. This is the running speed here. 20, 40, 60. Yeah, very small. This is, of course, another part of the bearing. That would be the outer race. But when I take a look at the bearing, if I look in kilowatts, I can start adding a quarter kilowatt here, half kilowatt here, 1.3 kilowatts here, 0.4 kilowatts here. Then I also have some impeller blade damage, so plus and minus twice line frequency, peaks associated with the blade. And then I can also take a look at that. In this case, that blade pass has a defect rating of about 2.9 kilowatts. What does that mean to me? Well, I can go in then and say, add them all together, 1.27 kilowatts here, total 4.22 kilowatts, total of the bearing and impeller, 5.5 kilowatts losses. So if I'm looking at that value times, say, a demand cost of $10 per kilowatt over 12 months, that's $660 per year. And then usage, let's say we're running around the clock 7 days a week, that's 8,760 hours, just so the number looks more impressive. 5.5 kilowatts times that value at 10 cents per kilowatt hour, that's $48.10 per year. Added together, that's $5,500 extra to run that motor per year. I can then, for the United States, it is 0.8 tons per megawatt hour for CO2. Actually, this has dropped down now to 0.707. So we'll just use 0.8 for this calculation. But this last year's 2020, it dropped down to 0.707 because we're not using as much energy. So 5.5 kilowatts times that value divided by 1,000 kilowatt hours per megawatt hour times that gives me 38.5 tons of CO2 per year that I'm dealing with that loss. Okay, so that's the end of the presentation. It's a good overview. You'll find lots and lots and lots of my papers online. I answer questions all the time in the technology. I really like people using it. To give you an idea, some of the studies we're in the middle of, this one here on the left, this is where I was last week. We're doing in-depth transformer and solar drive analysis, looking at the causes of some of the failures related to green energy. And then we have and this down here in the middle, that is a geothermal plant at the same site, looking at a lot of fans, 250 fans per stack. So a total of 500 fans. It's amazing. Just taking energy from the earth. Then on the right here, this is inside a tower. That's a salesman. I thought I'd prop him up with the equipment. But taking a look and seeing that entire powertrain I mentioned earlier, as well as the transformers, which may be at the base and once in a long while, the climb to the top. In any case, the concept here is that we are doing a lot of research in order to help improve the reliability of these machines by looking at total systems. And it's been quite amazing. So with that, that's from another presentation. The question is, do I provide specific training on electrical signature analysis? Yes. Of course, we're not all in person yet, so we do provide it online as well. I also have books and papers and everything else out, and other already available information out there on electrical signature analysis. It's really readily available. So does anybody have any additional questions? And I can't believe I did that in under an hour. I'm talking faster.
Oh, that's okay. It was great. It flowed really nicely. I love the addition of storytelling, and here just at the end too, some context on some real life applications that you're working on. Super interesting to hear. Howard, would you mind sharing your email or contact information in the chat, just so that people have a way to reach out to you if they do have any more questions? I know you're also available in the Slack community as well as you're on LinkedIn, but maybe a direct contact for you if you're comfortable with it would be awesome to share.
Yeah, I'll use the easy one. And then to get to me and my staff would just be info at. Perfect. And like I said, if you have questions, feel free. If you're using the technology, regardless of whose it is, if you have questions and you're seeing something that's puzzling, feel free to reach out. I probably run into it or know somebody who has and can provide an answer.
That's awesome. Well, if there's no additional questions from the audience right now, again, you can reach out to Howard here in the maintenance community or on LinkedIn as well. Thank you, Howard, for positioning yourself as such a great resource on this topic for all of these wonderful people here today and watching the replay, as well as just out in the maintenance industry in general. I think that will end our presentation for today. Howard, thank you once again for being here. Attendees, thank you so much as well. I hope everyone has a great rest of their day and a great weekend.
Yep. Thank you very much, everyone.
Awesome. Thanks so much. Bye.
Bye-bye.